We all learned about potential energy in school, lifting a book, that kind of thing. But have you ever really thought about how much energy it would take to completely escape Earth's gravity? Today, we're going to unravel a much more powerful version of potential energy, one that lets us calculate the journey not just up a hill, but all the way to infinity. Let's dive in. So here's how we're going to tackle this. We'll start with the simple stuff we already know. Then we'll see exactly why that simple stuff breaks down over long distances. From there, we'll get into the really clever workaround that physicists use. That'll lead us to the final, absolute energy formula. And maybe most importantly, we'll figure out what that little negative sign in the formula actually means. All right, first things first. Let's start on familiar ground, literally. We're going to quickly revisit the idea of potential energy, the way it works, right here, close to the surface of the Earth.
So what is potential energy, really? Well, at its heart, it's just stored up energy. Think about an apple hanging on a branch. It's not moving, but it has the potential to move, just because it's sitting inside Earth's gravitational field. The moment it falls, bam, that stored energy gets converted into the energy of motion. Pretty straightforward, right?
And for all the everyday stuff, we have this classic formula that you probably remember, PE equals mgh. It works perfectly for things like lifting a box or climbing a flight of stairs. And the reason it works so well is because over these short distances, the force of Earth's gravity is, for all practical purposes, constant.
But here's the catch. That simple, reliable formula has a huge blind spot. Things start to get really interesting when we stop thinking about climbing ladders and start thinking, well, a lot bigger.
I mean, what happens if you want to calculate the energy needed to launch a satellite into orbit or send a probe to Mars? All of a sudden, our friendly little MGH formula just doesn't work. It completely falls apart. And understanding why is the key to this whole puzzle.
See, down here on the ground, gravity feels the same everywhere. But as you travel farther and farther out into space, that force gets weaker and weaker. It's not a constant value anymore. It's continuously changing. So how in the world do you calculate the work you're doing against a force that never stays the same? That's the long-distance problem.
So what's the solution? Well, physicists came up with an incredibly elegant method. It's one of those ideas that's just so brilliant because it takes a seemingly impossible problem and makes it, well, almost easy.
The big idea is this. Instead of trying to calculate the entire journey all at once, you break it down into millions of tiny, manageable steps. And for each of those microscopic little steps, the force of gravity barely changes at all. It's pretty much constant. And if it's constant, we can use our simple rules to calculate the work done.
And this image shows it perfectly. It's like you're building a giant staircase to space. Each tiny step, which is labeled here as delta R, is so small that the gravity you feel at the bottom of the step is basically identical to the gravity at the top. You've turned one big complex curve into a whole bunch of tiny, easy, flat steps.
So our game plan is simple. Step 1, we slice the entire path up into tiny little pieces. Step 2, we calculate the work needed for just one of those tiny slices. And step 3, we add them all up to get the grand total.
Okay, so let's see how this actually builds our final formula. Now, don't worry, we're not going to get lost in a sea of algebra, but I want to show you how adding up all those tiny steps reveals a beautifully simple answer. So when you do the calculation for a single tiny step, let's say from point 1 to point 2, this is the formula you end up with. It looks a bit complicated, but it's just based on a few things: the universal gravitational constant, the masses of the Earth and the object, and the start and end points of that one tiny step.
Now for part 3 of our plan. We just add everything together. We take the work for the first step, add the work for the second step, then the third, and so on, all the way until we reach our final destination, point N.
And this is where the magic happens. When you line all those equations up, all the messy middle parts just cancel each other out. The end of the first calculation cancels the beginning of the second one, and that pattern just repeats. So all you're left with is the very beginning of the journey, R1, and the very end, Rn. It's incredibly clean.
Okay, now for the big conceptual leap, the real breakthrough. Instead of measuring from the ground or to some random point in space, what if we chose a universal reference point? What if we set our final destination at infinity? A place so mind-bogglingly far away that Earth's gravity literally drops to zero. That becomes our ultimate finish line.
And the great thing about using infinity is that it simplifies our math beautifully. I mean, think about it. What is 1 divided by a ridiculously huge number? For all practical purposes, it's 0. So that whole second term in our formula Poof, it just vanishes.
And this is what we're left with. Our final, elegant, and incredibly powerful formula. This is absolute potential energy. It gives us the exact amount of work needed to move an object from where it is right now all the way out to infinity until it's completely free from the gravitational field.
Okay, so we have our formula. It's beautiful, but you probably noticed that little negative sign hanging out in front. And you might be thinking, wait a minute, can you have negative energy? The answer is yes, and that negative sign isn't a mistake. It's actually the most important part of the entire story.
That minus sign tells us that we are bound by gravity. We're stuck in what physicists call a gravity well. The best way to think about it is like a debt. Because gravity is an attractive force, you owe energy to the universe to get out. You have to add energy to the system to pay off that debt and bring your energy level up to 0, which represents freedom. So as you get farther away, your energy actually increases because it's becoming less negative. So for any object sitting right here on the surface of the Earth, it's at the very bottom of that gravity well. Its absolute potential energy is at its most negative value. This represents the maximum possible energy debt it owes to the planet.
And this all leads to a final, pretty cool thought. If every single object on Earth has this massive energy debt that it needs to pay off just to break free and reach 0, it really makes you wonder, where do rockets get the colossal amount of energy required to pay off that cosmic debt and finally achieve liftoff? Something to think about.